this lecture, let us discuss about probabilistic context free grammars, also called as PCFGs. So we saw what is meant by ambiguity and what is syntactic ambiguity in parse trees, etc. So here ambiguous sentence or grammar, it leads to multiple parse trees, right? So in general, since natural languages are inherently ambiguous, at least for computers to understand, there are often cases where multiple parse trees are possible. So in such cases, have to figure out most likely parse tree. Say if we have multiple parse trees for a single sentence, then we need a way to make the algorithms figure out the most likely parse tree. So both top-down and bottom-up techniques that we have gone through so far will generate multiple parse trees. But none of the trees is grammatically incorrect, and also some of these are improbable to occur in normal conversation. So to identify which of these trees is the most probable one, we use the notion of probability. So here, probabilistic context-free grammars, they are mainly used when we want to find the most probable parse structure of a sentence. So simply we can say that when we want to find most probable parse structure of a sentence, then we need to use probabilistic context-free grammars. And here PCFGs, they are nothing but the grammar rules which are similar to what we have learned, that is the grammar rules which we learned in context-free grammars. These PCFGs are similar to the general context-free grammars. But along with that, here we'll learn probabilities. So we'll learn probabilities associated with each production rule. So let us see one example. Say suppose this is a production. NP derives determiner noun. So this is one combination we saw. Or it can be noun or it can be noun preposition phrase. So here in this case, along with the production rules, we are assigning probabilities. So probabilities are associated with each production rule. So it means that the probability of an NP breaking down to determiner and noun is 0.5. So we can read it like this. So probability of breaking down or probability of an NP breaking down to determiner and noun is 0.50, and to an N probability is 0.3, and preposition phrase is 0.20. So here make sure that sum of the probabilities of given production rule is 1. So if you add all these production rules, probabilities will get sum as 1. That is 0.5 plus 0.3 plus 0.2. It should give you 1. So this is a basic. Here let us take one more example. And in this we can see probabilistic context-free grammar. It looks the same as context-free grammar, right? But we have probabilities assigned to each rule in the grammar. So just like how we considered one example in our previous slide, here we are taking one more example where the probabilities are associated to each production rule in the grammar. Here I have a set of context-free rules and I'm assuming S as a start symbol under the context-free grammar. And also we have probabilities for each rule. So here I'm taking S as start symbol. So these probabilities, they have one critical property, that is, if we take any non-terminal in the grammar, say suppose verb phrase. So here Let me take 3 possibilities instead of just 2. So VP derives VI. And the probability associated with that is 0.6. Okay. So see this. Let's take VP. There are many possible ways of expanding that non-terminal, right? So VP can be extended in 3 different ways according to the productions given here. So we can write it as VP derives VI. This is one possibility. And it can be written as VP derives VT NP or VP derives VP PP. So we can write it in 3 different combinations or 3 different ways. So here we can notice that the 3 different probabilities associated with the 3 options sum to 1. So as we discussed just now, here when we add all these 3 possible values, it should give us 1. 0.6 plus 0.2 plus 0.2. That gives you 1. This is a key constraint on the probabilities in a probabilistic context free grammar. So if we look at any non-terminal, we must have these probabilities summing to 1. So if you take this combination NP, so here we have 2 combinations or 2 possibilities, and if you add these 2 values 0.8 plus 0.2, it should give you 1. So these probabilities, they have clear interpretations and they are the conditional probabilities conditioned on a particular non-terminal. So we have different ways of writing non-terminals here. So we now distribute those other options over those different ways of redirecting that non-terminal. So here, let us draw one particular parse tree using this grammar and assume that the sentence given for us is the dog sleeps. This is a sentence. Now we need to find out probability for this sentence by drawing parse tree. So first let me draw parse tree for this based on these productions. So here S derives. We have only one production. So S derives, we can write it as NP VP. Then NP derives. So this first rule is having highest probability. So, and according to the sentence also, we need determiner. So I'm taking determiner and noun. Then from this table, determiner is deriving the. And noun is deriving 4 words. But out of 4, dog is having highest probability. According to the sentence also, next word is dog. So let me take it as dog. And then VP. VP derives. So we have 3 different ways. So out of that, VP derives VI is having highest probability. And according to the sentence, we have verb. So let us take VI. And here from the table, VI derives sleep from table 2. Sleeps. So this is a parse tree which we considered or constructed from the given grammar. So from this, we can say that this is a valid parse tree under the underlying context free grammar. We'll now assign probabilities to this parse tree, which is simply product of possibilities for different rules. So if you take the first rule, S derives NPVP. So for that, it is having probability of 1.0, right? So here, let us write this as 1.0 into, then dt goes to, sorry, next one is NP goes to determiner and noun. So NP goes to determiner and noun. So what is the probability? It is 0.8. Next, determiner derives the. So probability is 1. So this one. Then noun derives dog. Probability is 0.5. Next, come to the right subtree. So VP derives VI. Where is it? VP derives VI and the probability associated with that production is 0.6. VI derives sleep. So VI derives sleep's probability is 1.0. So this is the final expression for this tree. So final expression, it looks something like this. So you can calculate or you can multiply all the values.